So is that clear? Can people see the screen? This is a tiny bit awkward. I want to position the laptop so I can see it while I talk, but I don't want to hide behind the podium. So, okay. So what I want to talk about today is partly kind of conceptual and partly sociological. There's a kind of puzzling situation in cognitive science, at least puzzling to me. That's kind of the collision of two zeitgeists that don't quite agree with each other, resulting in a mishmash of ideas in modern cognitive science that don't quite mesh with each other. And I need to kind of explain what's going on in cognitive science. I know most of you are not from a cognitive science background. Is anybody from a cognitive science background? Maybe not. So I'm going to start by giving a kind of quick update on what happened in cognitive science in the last 20 years, and then explain the problem. And the talk is structured as if you don't know anything about the philosophy of probability, which I realize is not true for some of you, and probably some of you know way more about it than I do, but I'm going to try to explain from the beginning some issues in philosophy of probability, but the main focus is on how they intersect with cognitive science, at least modern cognitive science. So the big story in the last 20 years in cognitive science is the rise of Bayesian cognitive science. Bayesian cognitive science is basically a collection of models which were first introduced in the early 90s, but basically become very popular in the last 15 years or so. That model perceptual processes and cognitive processes as kind of rational models where the idea is that the brain has certain priors and certain likelihood functions, and therefore has certain posterior functions, and assigns belief in a way that is approximately rational given the assumptions that it has. So I'm going to kind of briefly review what those models look like, but this is going to be sort of zooming through a literature of 9 billion papers. The big story for this slide is just that they've become extremely popular, and this is despite an earlier set of arguments against Bayesian models, originally due to Amos Tversky and Dan Kahneman, who very famously argued starting in the 1970s, but really famously in the 1980s, against Bayesian rational models of cognition. And this whole thing is sort of out of order. It's a little bit ahistorical because Kahneman and Tversky got very famous for these arguments at a time when, very famous for arguments against Bayesian cognitive science at a time when, to my knowledge, nobody had proposed Bayesian models of cognitive science. So I'll explain some of the arguments, both pro and con, in a minute. But when I was growing up in cognitive science, everybody had to learn evidence, mostly originally due to them, that people are not Bayesian. And it was a little bit odd because I never heard anybody say that they were. It turns out that basically people in economics had widely assumed that people are rational, and the implication was that they would obey, Bayesian principles, and Kahneman and Tversky were arguing against those. People in psychology largely had not proposed anything like that, and there's a long history in psychology of assuming that people's thoughts are largely irrational and kind of unsystematic, going back to Freud, who, in a totally different connection, proposed that people have kind of crazy, incoherent thoughts that are due to inner impulses that don't obey any principles of rationality at all. But of course we don't believe Freud anymore, but fast forwarding to the 1970s, nobody had exactly articulated a rational model of thinking or perceiving, but Kahneman and Tversky said that it can't work before anybody even tried. But then in the 1990s, people started to try, so I'm going to come back to some of these arguments later after I flesh out more of the pro side for cognitive science. But in the meantime, Bayesian models have been proposed for practically every aspect of cognition and perception, and mostly with great empirical success. So, categorization, memory, decision-making, reasoning, etc. Again, I'll give you a few tiny bit more specific examples in a minute. I do somewhat divide more cognitive issues from more perceptual ones, even though that division is possibly quite artificial. But the evidence for rational models in perception is generally more widely accepted and stronger than it is in things like categorization. But there's evidence in all of these things, and there's even a tremendous amount of Bayesian work in understanding the underlying neural code. So again, I don't have time to summarize all of these things because it spreads everywhere. But nowadays, in mathematically oriented approaches to neuroscience, there's this idea that neurons are actually transmitting through their spike trains, which used to be analyzed in totally biological terms, that are now thought of in information theoretic terms, where the modern analyses basically hold that if you interpret the spike trains that neurons flash with according to Bayesian principles, essentially they're very informationally efficient. They're transmitting information in a way that is practically at ceiling in terms of how efficiently information can be transmitted. So there's even Bayes' rule appears in papers about spike trains that don't even relate to perception or cognition very directly. It's everywhere. So again, I mean, I'm kind of saying this out of order, but all of these models propose that there's some observer in your visual system, your auditory system, your categorization system that is essentially a Bayesian reasoner, meaning that it has priors, it has likelihoods, and its beliefs, or if in an extended version of this theory, its actions are based on Bayes' rule or extensions of Bayes' rule. So let me give you a couple of like super fast examples. So in color perception, so color perception is a huge literature that had a lot of very vague ideas and principles in the hundreds of years that it's been studied up until the 1990s or 2000s. But in the 2000s, there have been some proposals that basically what it's doing when you try to interpret the color of a surface. So here you have some sense data, such as the combination of frequencies that are reflecting towards your eyes from the surface, and it's very ambiguous in the sense that you don't know what the reflectance properties of the surface are. That is what the actual color of the surface is, actual in quotes there, because it's essentially all happening in your mind. But there's a long tradition of understanding this is an ambiguous problem. So I'm not going to name names here, but some color theorists in the 2000s proposed that essentially you have a prior for the structure of surfaces, that some surfaces are more common in the environment or more plausible as hypotheses about surface structure than others, and that defines a prior over surfaces. And then you have a likelihood function for essentially the spectral content of the reflected light as a function of the true nature of the surface, and that's where the likelihood function would be set up in this. And then you have a posterior based on Bayes' rule, and I'm going to assume that everybody knows what Bayes' rule is, but based on rational principles of probability theory that says what the reflectance is likely to be, and you get some posterior well, one thing I'm establishing is the idea that the mind embodies properties of the world has become universal gospel in cognitive science, especially in perception. But exactly what that means is very unclear. And these people all have different ideas about what it means. So one specific idea about what it means that especially Bill Geisler at the end has advocated for is what's sometimes called natural image statistics. This is a term for perception. You'd have to extrapolate it a little bit to the rest of cognition. But it's basically the idea that in order to figure out what the prior should be, this is the beginning of the answer to Harry's question, what you should do is look at the world. So if you want to know what the prior over surface is, in the color example that I gave before, the prior over colored surfaces, go to an image database, and nowadays we have these huge image databases, and count the colors. Like, in other words, you know, what proportion reds, or it's of course more specific than that, but you get some distribution, which is then, everybody knows the database is not perfectly representative of the world, but aside from that, that's a good estimate of the natural frequencies in the world, and therefore a good estimate of the objective naturally occurring probabilities in the world. This has become a hugely influential idea. I mean, one aspect of it is the modern emphasis on huge databases in like everything, in cognitive science and machine learning and statistics, where everybody wants to look at huge databases to tune up their learners. And behind that idea, the slightly more academically rigorous idea, is that those databases tell you what the prior should be, or what the probabilities are more generally. So the assumption implicit in most of this work is that the correct prior for some event or predicate X is the relative frequency of X in the world. Okay. Furthermore, in arguments about Bayesian models, this is often seen as the most legitimate source for the prior. I mean, this is ironically most prominent in a lot of people who criticize Bayesian theories, who basically often argue that Bayesian models are often somewhat arbitrary in their priors, but at least sometimes they get it right by appealing to the natural world as the source of the prior. Anti-Bayesians often say that. And then in the pro-Bayesian world, there's kind of half the world that does this, and then half that does something else, which I'll get to in a second. Okay. So just summarizing all this, there's now what I regard as a conventional wisdom in the field, which is that, in terms of the nature of probability, that we assume that event classes have true probabilities, which are their relative frequency of whatever it is we're talking about in the environment, like the relative frequency of the color red in the environment, or whatever it is. And agents are optimal when they have those priors. Geisler, for example, has a whole story about how agents are well, I guess this is the next bullet, how natural selection pushes agents towards the true prior. So in other words, if you have an agent that is like some animal that's at some point in its evolution, and it innately has the wrong prior, evolution is going to push it towards the right prior in the environment that it's in, because that's the only way to get the right answer, or to be optimal. So if there's some other agent that's closer to optimal, then it's going to get better answers, and it's going to survive better and make better, more offspring, the usual adaptive story. So all of this is premised on the idea that there's a true probability. Right, are you with me? So the problem with this, which I think is the next, is that that's actually not the standard position of Bayesians. I mean, when I say problem, I mean the inconsistency. So this is where I realize most of you are probably very familiar with this, but let me just introduce it in a certain way. So there's a long history of debate in statistics and philosophy, and eventually in the Bayesian literature, but not so much in the modern cognitive science literature, about the nature of probability. And the idea that there's a true probability in the environment, or a true statistics of the environment, is actually a very strange idea from a Bayesian point of view. It's not what Bayesians traditionally think. So Bayesians traditionally hold this view that's sometimes called subjective or subjectivist. I prefer to call it epistemic, the same basic idea. An epistemic view of probability, in which probability is degree of belief. And the idea is that probability theory is about quantifying the degree of belief in the mind of an observer, not about relative frequency, as opposed to frequentists. Fisher is the most famous in the statistics that psychologists cite anyway, who think of probability as relative frequency in the limit as you go to infinity. So you have some event, like you select a surface, and then you do it an infinite number of times, so asymptotically in the limit, and you just count the relative frequency of the event, like it being red or something like that, and that's the probability.
Just a historical tidbit.
Yeah.
Yes, Mises was a frequentist, but he was also a Bayesian.
I didn't know that. I've read part of his book. I didn't. very interesting. Okay, so let me say in that connection, I hesitate to put this debate into two camps because there are as many different views of probability as there are probability theorists, and no two people have exactly the same combination of views. I myself, when I've done historical reading of this, I'm always surprised to find that this or that author who's famous for view X actually said something else or something quite a bit more complicated when you read it. So I'm not a historian, but it's quite common.
But von Mises didn't talk about that in his book, did he?
Well, yes, a little bit. It wasn't emphasized. But for example, he wrote a paper in 1942 about the correct way to use Bayes' rule.
That doesn't make you a Bayesian.
Yeah, Fisher wrote about how to use Bayes' rule as well, but he didn't think you should do it when interpreting data from scientific experiments.
Von Mises criticized Fisher for not using Bayes' rule.
Really? I would love to read that, but you know far more about the history than me.
Does von Mises think that the Bayesian price probability should track frequencies?
Yes, there should all be frequencies.
But you still use update rules of Bayes?
Yes.
But isn't Bayes' rule just a rule of calculating a conditional probability? It has nothing to do with the
Well, Bayes'
interpretation
theorem,
of probability.
Given like cross time.
yes, you could treat Bayes' theorem as something
That's uncontroversial. Yeah. No, that's exactly the issue. Though. So I want to explain why this matters to Bayesians traditionally, but the main point is how this applies in cognitive science, which is the less clear part. The main part I wanted to pull out from this dichotomy, so it is only two views, and there are of course more than two views of probability, is that Bayesians traditionally, mostly, and there's always controversy about this, think of probability as a characteristic of the observer. And frequentists generally think, this is even less 100% true, but think about probability as a characteristic of the world. Von Mises went out of his way to define ensembles in such a way so that he could say that. That's all I understand about Von Mises. But the idea that probability is simply relative frequency is entails that it's an objective characteristic of the world. And the kind of big sociological point that I want to make in this talk, just to make it clear where I'm going with this, is that most modern psychologists are unconsciously frequentists because we've been trained that way, and maybe for other reasons. And the fact that that sort of conflicts with Bayesian philosophy of probability hasn't quite come to a head in the field. And there's a conflict that is kind of fundamental in my view. So the issue here is that if Bayesians are right, there are no true probabilities in the world, and it doesn't make any sense to look at a database to find out what the true ones are, because there are no true ones. Instead, there's something else, which part of the point of this talk is to paint what I think else there might be. Okay.
What about the kind of hybrid version, reconciliation frequencies and Bayes' rule? So you like David Lewis and Barry Lower, you think that one way to ground the data probabilities is in frequencies, but you should kind of match the priors to the...
So let me first, generally there are many intermediate positions like Popper, et cetera, but I'm not going to get into
So this is not Popper's.
I know. I just say there are many intermediate views. The issue of how probabilities are grounded in observable data, of course, that's a standard part of Bayesian theory. It's not like Bayesian think you just make everything up. And so the issue of exactly how the epistemic probabilities are related to observations in a perceptual situation, again, that's one of the things I'll be talking about. So I mean, I'm not going to, I don't know exactly how it relates to various views, but.
Yeah, I think that will be a third view in which you can kind of reconciliate frequencies position, which is what psychology production train, and also the more Bayesian way of thinking.
Quite possibly. I mean, I'm not saying there isn't a reconciliation. One of my points here is sociological, that this is something that the field hasn't grappled with yet. Well, so let me just say a little bit about why, why subjectivism is important to Bayesian. So this is probably not necessary for this audience, but for most people in psychology that I explain this distinction to, it's not clear what's at stake because it seems like a philosophical, quote-unquote, philosophical difference. But the whole point of the difference is that if you want to use Bayes' rule, this is the issue of what we were just talking about a minute ago. Bayes' rule is just a theorem that no one can really argue with. The question is, how do you use it, or how is it reasonable to apply it? And to Bayesians, you want to apply it to figure out the value of some state of nature. And frequentists refrain from doing that because of their view of the appropriate situation in which probability can be assigned. So to frequentists, probability can only be assigned essentially to random quantities, that is, quantities that vary
such that you can repeat some experiment and they come out a different way at different times. Like in Fisher, the classic example is random samples. You draw random samples, and every time you draw a sample, you get some different properties, like a different mean, and that's quote unquote random. And so then you get random variables and a distribution over those. But frequentists like Fisher didn't want to assign probabilities to things like the truth or falsity of a theory, because that's a fixed quality of the world that we simply don't know. But to Bayesians, they don't mind that it's a fixed quality. They're still willing to assign probabilities to it because the probabilities are epistemic. If I assign a 72% chance that your theory is true, that doesn't mean it's true 72% of the time. It means I'm 72% confident that it's true. And that's what Bayes' rule tells you, if you have appropriate priors, et cetera. And that's perfectly fine if you're epistemic. So if you want to assign some truth value, some probability truth value, to the truth of a theory, for example, then you have to adopt an epistemic view of probability. Otherwise, it makes no sense to assign probabilities to the truth of the theory. And the thing is, that extends to just about anything, at least anything in cognitive science that you would want to assign probabilities to. So if you're a perceiver and you want to figure out the distance to that wall, or the color of that wall, or anything, that's a fixed value in the world, at least at this exact moment in time it is. But it's something I might have variable belief in, or I might believe it's some gray or something, and some distribution of belief over that, and that's a perfectly valid epistemic from an epistemic point of view. But if you're a frequentist, you wouldn't be assigning probabilities to the different colors of the wall, because the wall actually only has one color, and you can't repeat it to get different probabilities. So fixed physical quantities is the most extreme example. I mean, I'm saying it in a perceptual context, but the most famous examples of these are actual physics. Like if physicists are trying to figure out the mass of a proton, that's one fixed number that they simply don't know. And from a Bayesian point of view, an epistemic point of view, you can assign a probability distribution based on experimental data. But from a frequentist point of view, you can't. That's the traditional dichotomy. There are a million gradations in that, but that's why Bayesians want to be epistemicists. The truth of theories, that's what I meant by the Fisher example. So this is going to kind of set the story. In the subjectivist framework, probability is an epistemic quantity. It's not an objective characteristic of the world, and therefore there is no single correct value of it. And the prospect of grounding cognitive science, perception theories, for example, in the true probabilities in the world simply doesn't make any sense. And that's the kind of sociological puzzle. So let me just illustrate some of these ideas with coin tossing example. So, I mean, this is just the example that I have when I'm explaining this to newcomers, which I realize you folks are not. But when you think about the true probability of heads on the next coin toss, most people feel subjectively very strongly that there is kind of a true number, right? So a typical coin is 50%, and it's a little bit strange to think that it isn't really 50%, that's like just in your mind, because the coin has physical characteristics that seem to make it be 50%. And so therefore, that seems like a fairly objective fact about the coin. And the epistemic argument is essentially that that's not true. So I want to work through that a little bit. So first of all, when people think of this example, they always think in terms of a fair coin. But when you define a fair coin, of course, you have to be very careful not to define it as a coin that has 50% probability of heads, because then it's completely circular to say whether it's true that it has 50% probability of heads. And when people think of the example, they're usually thinking about that example, so it's very misleading. You have to think instead about a coin that has kind of an arbitrary heads probability. And so you observe a coin a certain number of times, and it hits heads a certain fraction of those times. And the question is, what is the true probability of that coin? And there, it's a little bit easier to see the intuition that it's not clear that there is an objective answer to that. So again, the frequency idea is that it's a long-run frequency of heads, meaning that if you took that physical coin and ran it under identical conditions an infinite number of times, or find a very large number of times, that the proportion of heads it comes up is the probability. But that's making a number of assumptions that are not quite fair. So from a subjectivist point of view, it's a state of belief, and to preview where I'm going with this, it depends on what the observer knows about the coin or thinks about the coin. So the obvious example is, what if the coin is being flipped and one person has accurate information about the coin that other people in the room don't have. So I flip a coin right now, and one of you happens to know that I'm using a coin with 2 heads. So you would correctly assess the probability of heads as 100%, whereas everybody else thinks it's 50%. Who's right? in that example, the person who knows that it has two heads might be right. But if you take a weaker example, like I flip a coin and some of you think it's 50-50 coming up with heads, but one of you happens to see the coin flip by, as it reaches its apex, and you see that its head's at its apex, and you have very sharp eyes. You realize that actually biases it somewhat. It's more likely to be, to be heads, let's say, as it comes down. Maybe you think it's 0.7. So are you right or are you wrong? That depends on whether that model of coin rotations is actually accurate. Because of course the coin is not really, a non-deterministic, repeatable, infinitely repeatable trial as in the frequentist conception. It's really a physical process that is either going to come out heads or come out tails. And what you know about the mechanics of or details of that process are going to affect your estimate. And different observers will have different information and therefore give different estimates. And the epistemic argument, which I'm going to flesh out somewhat, is that different estimates are impossible to rank in terms of which one is more right and which ones are more wrong. Go ahead.
You might be just about to get to this, but one intuition I have when you're describing this coin case and you're varying these parameters is you're varying the reference class of trials that we're considering.
That's 100% right.
And someone who thinks that there are these true probabilities might think that there's a true probability of this coin landing heads relative to this reference class, and a true probability of this coin landing heads relative to this other reference class. So when you start introducing more information in something, that might change the reference class, but that doesn't seem to me like, I don't know if your point here is to say that it's a little bit, I don't know whether exactly you're trying to argue that we can't really make sense of there being a true probability of heads, and so I don't want to.
The argument, so let me, if I can restate your point.
Yeah.
The probability depends on the reference class and maybe a few other things, but there isn't a single objectively correct reference class. Different observers are going to have different beliefs about what the reference class is, and that's going to change their values, and the epistemic argument essentially is that there's no way to adjudicate among them.
But that doesn't mean that there aren't a bunch of these objective probability values and each is indexed to a reference class.
Yeah, but that would defeat the entire program of objective values of probabilities. But I mean,
okay, that's the step I think I want to hear. Just I get the idea, but can you elaborate a little bit on that last thing, or move on?
Well, I'm trying to think if what I'm going to move on to is going to address your point. Maybe, I mean, part of what I'm going to move on to definitely is about reference classes and language. So let me see if it answers your question.
Okay.
Related to this, so I think James as a paradigm Bayesian in the objective sense, he thinks that the question has to be well posed, given enough information about what's going on in the system and environment.
Right.
So you might think that there are different probabilities, conditional probabilities. Given this amount of information, this is probability the correct one.
Right. I mean,
so would you say supports this, or there is no probability?
Well, okay, so I'm going to be a little more explicit in a minute about differences among observers. James's argument, for those of you who aren't familiar with it, is that essentially every rational observer who has the same information should arrive at the same probabilities. And I don't agree with that, but
that is consistent with your description about various.
Yeah, simply because there are other differences between observers. But let me just say, I'm an epistemicist, but my main point in the talk is not to convince people to be an epistemicist, but to simply say there's a conflict between, the talk is in that sense primarily sociological. I want to explain the conflict between the attitudes which I find to be inconsistent. I personally am convinced by the epistemic arguments, but that's not the main, well, actually, that is the main point of part of the talk, so, but I think kind of in a slightly different way from the normal arguments. Okay, so let me explain, again, this is sort of for newcomers. For people in psychology who are very brought up in frequentism, it is often very hard to explain where Bayesians, traditional Bayesians, get their priors from, if not counting things in the world, because that's the way it's usually expressed. The prior is often expressed as, to newcomers, as the proportion of times that a theory is correct, or the proportion of time that a certain condition happens in the world, which is a very frequentist way of saying it. And that distinction is never explained. So to newcomers, I often have to explain where on earth would you get the prior from if you couldn't count things. For example, the anti-Bayesians I mentioned a few minutes ago, the reason why they're praising Bayesian theories that collect priors from image statistics is because they think that's the only way to get priors, because they're frequentists. But so let me just give you a couple of brief answers. I mean, broadly, the answer is symmetry principles. Bayesians have a lot of symmetry principles. James is the most famous example. The principle of indifference is the original example from Laplace, where you think the coin is 50-50 probability because the two sides of the coin are symmetrical, and there's no reason to prefer one side to the other. No reason to assign one side a higher probability because you can't even tell the difference between the two sides. If there are differences, then you begin to wonder if they could have different probabilities. But if it's a perfectly plain coin, it's hard to imagine on what basis it could have a probability other than 0.5. So James has this maximum entry principle, which is kind of a very complicated version of the same basic idea, that once you have some physical constraints in the problem, they define a range of probability distributions, and you should, there's sort of an information theoretic argument to choosing a distribution which has the maximum entropy relative to those constraints. And that idea has had a huge influence because it supplies an answer to where to get the prior from when you don't have frequencies or don't care about frequencies. But the other answer, which often gets buried in this discussion, is simply previous inferences. The prior is not simply what you start with at the very beginning. The prior that you apply to a particular problem is whatever you learned from previous data from that, maybe from that same problem. So the famous cliche about this is today's posterior is tomorrow's prior, which basically says as you're moving through a series of data, you have your posterior that's evolving, and the prior for the next trial could be the posterior derived from the previous trial. So there's no great mystery as to where you get prior from. You learned it from the data. So again, that sort of addresses what somebody said before about connecting the data to the epistemic beliefs. Of course, they are very closely tied to the epistemic beliefs are very closely tied to the data through this basic idea.
So,
in cognitive science,
So I'm a little confused about who is and isn't a Bayesian by what you were talking about.
it's very.
Would the same slide apply to the likelihoods? Where do Bayesians get the likelihoods of not work?
That's an excellent question. To be honest, when I myself do Bayesian theories, I find that in order to construct the likelihood function, you have to apply similar ideas. Meaning you have to think about generative model from a sort of subjectivist point of view. But it's not usually expressed that way. So people have huge debates about where the prior comes from. They almost never in cognitive science have debates about where the likelihood function comes from. In my view, the issues are fairly similar. I mean, why people ignore the likelihood is itself a long story to.
I think the sociology you're describing is, Harry maybe might have been opinion, I don't know, but what you're describing is not so different than what's going on in statistics.
Really, that's interesting. I mean,
Is that fair? I mean, the so-called Bayesians have an objective interpretation of the likelihood.
Yeah, I don't see much difference between Bayesians and frequentists, except that they use that they put a prior on things.
Yeah.
Prior doesn't mean anything to them beyond.
yeah. There's a lot of truth there. So, but a related point addressing the other thing you said is that who's a Bayesian and who isn't depends on how you look at it, what you think a Bayesian is, right? So in cognitive science, there are a lot of people who do Bayesian work in a way that is similar to the way statisticians and sort of physicists like Jeffries did Bayes, and are epistemic in their adoption of priors, and they do things like this. And there are many other Bayesians who do what I'm implicitly criticizing, adopting priors in a very frequentist kind of way. I mean, the result, I was chatting about this with a fellow perception person. He said, yeah, a lot of people in perception are frequentist Bayesians. And we have to laugh about it, but it's true. There are many frequentist Bayesians in the
The
field.
word Bayesian was not invented until about 1960. And yet these same arguments have been going on, and the same overlap has been going on since the past.
Yeah, the difference in cognitive science is that people are ignorant of the history.
Well, they're ignorant in their statistics too.
That's not, that I can't comment on. But I mean, when I read Lindley or something, I mean, he read Laplace and Jeffries, right? Whereas people in modern cognitive science often
Yeah.
will
The
come to
point I wanted to make was that the sort of before 1950, well, let's say before Fisher, before 1920, this was very fluid.
Yeah, oh yeah, yeah.
So it was really it was kind of a middle of the 20th century. You had this sort of Bayesian versus non-Bayesian.
Yeah, no, I think that arose because of Fisher. And
Fisher had a lot to do with it.
yeah, I mean, because he adopted a strong position where others had, as you said, been more fluid.
Yeah, but then the Bayesian sort of reaction was also equally dogmatic. So I think we're kind of returning to the 19th century. in terms of people
Back to the Future. I mean,
not making these, sort of being willing to use, go back and forth, and
well, let me just say one kind of sum up point. So, in a sense, in Bayesian in cognitive science, people are recapitulating these old arguments. That certainly is the main thrust of what I'm saying. But there is a difference, which is that in cognitive science, we're actually trying to model people's beliefs. Whereas in statistics, the idea of epistemic beliefs was sort of an abstraction, meaning a philosophical position about the nature of the observer. In perception, or in cognition, we are literally trying to understand what people believe. And so, in that sense, it makes direct sense to think about
I'm
this.
slowing you down, but this,
Yeah.
there's a question I've been wanting to ask for a little while, which is because we just came out of a seminar where Barry was imposing or insisting on this sort of Ramsey Finetti savage interpretation of what belief is.
Mhm.
And that seems to be very embedded in philosophy now, that, degree of belief means how you cash it out in embeddings.
Embedding, yeah. Reveal preferences.
Is that the way your psychologists are thinking about it when you're talking about it?
Honestly, it's not usually expressed that carefully.
Not that careful.
So in perception, a belief is whatever the subject reports that they see. But in Bayesian models of perception, we're often not using subjective reports, but often using performance, where the performance is predicted on a model where they believe such a thing. So in other words, if they believe it's red, then they're going to respond such and such a way. And so the Bayesian account is supported to the degree that the kind of implied loss function implying a sort of action decision consistent with Bayes' rule predicts the responses that they make.
But the action decision is in choosing a reward or...
Well, it's usually pressing a button to say that they saw something, that something was larger than something else, or something was a different color than something else, or something like that. I think there's a
So
thousand.
this, I guess, but it's not usually cashed out in rewards or losses.
Well, there's a movement in that direction in the contemporary literature because there's more appreciation, now we're talking about the last 10 years, that to really tie belief to action, you need to put in a loss function or some sort of payoff matrix. And in order to really express a quote-unquote Bayesian theory all the way down to the responses, you need that component. But relatively few people have discussed that specifically. But the ones who do are definitely making progress. Okay. So this is, okay, so answering somebody's question from before, in the way I'm going to talk about it for the rest of the talk, observers can be different in a number of ways. So why would observers in a coin situation have different beliefs about heads? One is that they have different generative models. For example, one of the reasons that people watch a series of coins come up heads and think the probability is such and such is because they're implicitly assuming like an IID model. They're assuming that there's a series of independent tosses and that therefore it follows by pretty simple mathematics that the best estimate of the true probability of heads is like the average rate at which heads comes up. But that's not the only possible model you could adopt for the coin. Remember, we're not really talking about an actual coin. It could be anything that comes up heads or tails or two values. So I'll give you an example in a second. But there are also different epistemic conditions, like the example that I gave a minute ago, where one person is just watching the coin flips, another person is watching the coin flips, and a light glint off of it, another person knows something else about the coin, somebody else is watching a different light glint off of it. They have different information. Observers are going to differ in that way. The former one, like this is something that I don't think James recognizes people can differ in. This is more just like different information, which he would say if they have the same information, they should come to the same probability. And it's also worth mentioning, although I'm not going to say anything else about it, that different agents are not just forming beliefs, but also deciding what to do. And of course, they have different goals and different loss functions. Like if they're trying to estimate some value, they're going to have different penalties for being wrong in different directions. And that's going to lead to different beliefs as well, or can lead to different beliefs as well. So let me just break this down in a little bit more detail. So this is our coin again. And so you imagine it has some long series of zeros and ones, one being heads and zero being tails. And the question is, what is the probability of the n+1th trial, right? That's the coin situation as I described. So just fleshing out a little bit what I said in the previous slide. If you have an IID model, you would think that here, I've done the math for you, there are 28 heads out of 66 tosses. So you would think that the probability of heads is about 0.42. Not that it's exactly 0.42 necessarily, but you think that that's a good estimate. And that's right if you adopt the IID model, right? So independent model. So in this example, which I've contrived to make it come out a different way, you also could think that this is the Morse code for the first words of the Gettysburg Address for 7 years ago, and take my word for it, it is the beginning of that. And so you would think that the next, once you figure that out, of course, you're going to have pretty high confidence, nearly 100%, that the next one is going to be the first code item in the next word, which is what, I think?
Hour.
What did I say? Hour, yeah, hour, sorry. So, so the probability of 1 is approximately 1, it's supposed to be approximately. So because, I mean, I looked it up, and that's what the answer is. And so if you inferred that model, which is highly non-IID, right? It's extremely sequential, very strong sequential structure. You would think that it's almost certain to be a 1, and the first person would think you were nuts, right? But the second person is pretty confident that they're right, that the next one is going to be 1. Of course, they don't know for sure, but their estimate is rational, conditioned on the model that they have for the generative process. Okay, so so that's an important difference between observers. I want to mostly focus on the other difference, or an other difference, which is different sources of information. So here's a shorter version. So so this is the thing you're trying to estimate. The question mark is supposed to be the next place. You're trying to estimate 0 or 1 on the next one. And let's say one observer has another channel, like we'll just call it A. So I'm going to call the channels A, B, C, etc. X is the mystery one you're trying to estimate. So A has some other channel that says that when the 1 came along, a 0 also came along. When the 0 came along, a 0 came along the A channel, etc. And then they can use this to try to estimate what's going to happen on the n+1. So in this imaginary thought experiment, you know what A says on the latest trial, on the n+1th trial, but you don't know X. So whatever machine learning you want to do, or whatever patterns you can spot on all the previous trials that you have, you can use those to figure out what you think X is likely to be on the n+1th trial. Is that clear? So it's unclear whether it's a prior or likelihood. It's just a probability, meaning that you, on the basis of all the evidence that you have, you having the A channel, what do you think X is? And what do you think P of X is on that trial? Of course, it might be higher than an IID person who only had the X channel might think, or might be lower, depending on what you've included, but it's going to be different. And you would be perfectly justified in thinking that you had better information and therefore a more truthful estimate of the probability. Now, let's say there's another channel, B. You can imagine an observer who has only B and X. Everybody has X. Or maybe they have A and B. And you're going to get different estimates from every combination. But this is the classes you were talking about, right? So that's like the main argument here. So et cetera, et cetera, et cetera. And there's a potentially infinite number of other channels. Whether it's infinite or not depends on your assumptions about the size of the universe. But there's a lot of other channels, and some of them are going to help you out in your estimate of what X is, and some of them are not going to help you out depending on how your pattern recognition system works. Of course, that's highly contingent on how the observer actually works. But some of them are going to make your estimate go up, some of them are going to make your estimate go down. The question about the objective truth of probabilities has to do with whether you can think about them as all converging on some truth that, somebody who had all the information in the world, like God, who I'll mention later in the talk, might have thought. Okay, and the argument, to sort of preview where I'm going with this, is that it's kind of intuitively tempting to think that if you had all the information in the world, you would eventually converge on the true answer. And it's arguable that if you had literally all the information in the world, you would converge on the true answer. But if you have a finite subset of these other channels, you do not necessarily converge on the true answer if there is one. And that's kind of the argument, at least a slightly novel mathematical argument, for the epistemic view that I'm going to spell out a little bit. So sorry for the left font, but there's various other additional information to conditionalize on. Let me just express this in a particular way. If you go back to just X, there's a long history of debate about the nature of the limit what I'm going to call here the horizontal limit. So this is the limit of the relative frequency of ones as a portion of the total number of flips as you go to infinity. That's the traditional frequentist conception of relative frequency in the limit. So that's horizontal in the sense that I've laid it out on the board. As you go to more and more data, the question is, does that converge to something, and what does it converge to? Fisher and frequentists assume that it converges to something. Mies was a little more careful about the conditions under which it converges. But Bayesians have often criticized that, like James has this criticism where it's crazy to he would say as a physicist that it's crazy to think about the limit of a sequence when you have no idea if that sequence even converges. And meaning from a physical point of view, you would never do that. You would never assume some limit has a limiting value, some sequence rather has a limiting value, if you don't even know mathematically whether it converges or not. I mean, from my perspective, it's a little strange way to put it, because this is not actually a mathematical sequence, it's an empirical sequence, meaning you're imagining an empirical sequence of coin flips, and you, of course, no way of knowing if it's going to converge, because you don't even know if the coin is going to change properties or whatever. It's kind of meaningless, at least from an epistemic point of view, to say that eventually that sequence of coin flips is going to settle down to some particular relative frequency, because for all you know, it'll start being ones all the time as the coin changed. But putting that argument aside, the argument that I'm talking about here is whether the what I'll call the vertical limit exists, which is as you add more channels, you eventually converge on a probability estimate that is quote unquote truthful, and that's a completely orthogonal, literally orthogonal question, which is what I want to address. So I guess I attribute that. I think James was quoting Jeffries in that argument. So let me say something about an observer. So I'm going to refer to an observer. I'm going to call an observer every distinct combination of channels. A very, very simplistic way of viewing what an observer is, but it's supposed to capture the idea that different observers know different things about the coin. You have some that know A and B, some that know C and D, some that know A, B, C, and D, whatever. So essentially every subset of all the channels is a distinct observer. What I'm basically going to show you, as I just said, is probability is not monotonic in channels, meaning really supersets of channels. And therefore, every observer, this answers your question before, every observer is going to have essentially a different rational probability, which the argument is that kind of does away with the idea that there's one correct probability, unless there is one correct observer, which is, I think, a perfectly valid perspective if you were very religious, because the correct observer would be God. But I mean, so I had a joke somewhere on one of these slides. So that prior, I refer to one of these papers as the Lord's prior, because I can't resist a pun. But people often call it the God's eye prior, right? It's the prior from the point of view of God. And unless you think God is in on this discussion, then all finite observers don't have, they just have different probabilities. Okay, so let me go through like one more slide, or two more slides. And then, I mean, this is exactly what you're asking for. So one way to look at this is to look at the lattice of subsets, which is a simple, construct. How to look at the relationships among different subsets. So again, now each of these subsets is a set of channels with ABC at the top. So I'm imagining there are only 3 variables in this world plus X, which is the 4th variable. And so different observers either have just X, which means that they have no other information, or they have all of it, which makes them God in this universe, or they have various subsets. So, I mean, the first kind of obvious point about this is that these subsets, don't always overlap. And so observers are going to not just have different viewpoints, but viewpoints that are sort of incommensurate. So I'll explain what I mean by the term in a second. Each observer is a different combination of channels. The global supremum, that is the one at the very top, knows everything. And if you could imagine an infinite number of channels, like the entire world, or a huge finite number, if you don't think the world is infinite, then God knows them all. And down here, we just think of the prior as being, if you just measure the one variable and nothing else. And in Bayesian cognitive science, people often express the correct prior. People who are more frequentist in the attitude express it that way, that the prior is what you get if you ignore all the other variables in the universe and just collect data on this one channel. You'll get the true prior for that channel. And that's a sort of perfectly well-formed idea, but it's down here. So the punchline of this is kind of already stated already. To me, it's mathematically obvious and not like a deep point. It's just a way of looking at it that's novel. Is that you have 2 different kinds of observers, of observer pairs here. Commensurate observers, which are observers where one is a subset of the other. In that case, you have an observer who knows, let's say, B, and another observer who knows B also, but knows more. This observer is, in a sense, more expert than this one. They know more, right? They're commensurate in that sense, and you can compare their knowledge bases in an ordered way. One of them literally knows more than the other in the sense that they're a proper superset of the other, right? But then there are other observers like A, B, and AC, and I could have circled a lot of other examples on board, are incommensurate in the sense that this one knows certain things, And this one knows some other things. They do have a common element, but they don't have all common elements. So you can't say that one is more expert than the other.